Hey guys, Mr. Gibson here. I'm going to show you guys how to write equations from tables of functions. Okay, so 3 ways to represent a function: equations, graphs, tables. We've done some work from graphs to equations, graphs to tables. Y'all are pretty familiar with that from previous years, but we're going to take a table and make a function. Okay. Our first example is a linear function. Okay. And how you can tell it's linear is look at the outputs. I find this difference, what I call the first difference, and it's all the same. The first difference is 2. Notice on top the first difference here, we're going up by intervals of 1. Okay, we're just going up by 1 on the x value each time. That would make a difference if you didn't. We're not going to really worry about that in that video. This is out of our scope today. Okay. So if you have the same first difference, that means you have a linear function, and better yet, you have a slope of 2. Okay, so we're going to use y equals mx plus b to plug this in, but we're still missing b. B is our y-intercept. Well, we know that when x is 0, that's our y-intercept. But we don't have x is 0 here, so what we're going to have to do is take this and use the same pattern and go backwards. So we go from 3, 9, 2, 7, 1, 5, 0, 3. So we went back by -2, okay? Keeping that same first difference. Well, there you go. We've got all our information. So I know f of x here is slope of 2, 2x plus 3. Okay, that's a linear example. Next, we have we're actually going to go through 2 exponential examples because I want to talk about something with exponentials also. Notice here, these numbers climb very quickly. If I see that, then I figure it's going to be an exponential. Okay, and also these are all divisible by 3. So I figured out that each time we're multiplying by 3, okay? So we'd actually call this exponential growth, all right? Now, we call this times 3, we call it a common ratio. If the common ratio is greater than 1, we're going to have exponential growth. I just wanted to mention that. We also have this nice little formula for a exponential equation, putting it together from a table. We know the common ratio, we know this number right here, but we have to find the y-intercept. All right, so just like we did with the linear, we're going to go back to 0, but instead of using a first difference and subtracting back, we're going to use a common ratio and divide back to 0. Okay, so we go from 2 to 1, we're going to divide 18 by 3, get 6, and then we take 6, divide it by 3, and we get 2 to get back to the 0 place of this function. So we know that the y-intercept is 2. There's our function. Y-intercept 2 times 3, the common ratio, raised to the x. Okay, exponential growth example. Let's look at another exponential example here. Now, all of these are divisible by 4, but as we go up, okay, so these are negative numbers, we go into the positive numbers with our x. As we go up, we're not multiplying or getting bigger, we're actually getting smaller. And if you look, we're dividing by 4 each time, at each step here, okay? So our common ratio is dividing by 4. Now, the same thing as dividing by 4 is timesing by 1/4, okay? So that gives us a common ratio of 1/4. Now here, I don't have to do as much work to find this this y-intercept point. We know it's 2 because look, there you go, 0, 2. We're done there. The final thing to say is if this number, if this common ratio is greater than 0 or less than 1, it's like sort of fraction there, a fraction less than 1, then we have exponential decay, meaning it gets smaller and smaller and smaller. When something decays, it gets smaller. All right, finally, we've got quadratics, and they're a little more involved. So let me take you through a couple things here. So first of all, I want us to notice a quadratic has this form right here. This is the standard form of a quadratic equation. And we want to find out what a, b, and c are. Okay? The first thing I want you to notice is when x equals 0, so I plug in 0 right here, this just equals c. So c is more or less it is your y-intercept. Okay? Now I put a sample function in here to show you a few things. So my sample function is y equals or whatever, f of x equals 4x squared. All right, that gives me these outputs right here. So I find the first difference. Well, it's not linear, so the first difference isn't the same. That doesn't really tell me much. So then I take the second difference. So the difference of the first difference, look, they're all the same. If the second difference is the same, it's a quadratic. Also, look, this is 8. 4 times 2 is 8, okay? So the second difference is related to A by being half of A, or double A, or A times 2, okay? So 4 times 2 is 8. A, as in 4 times 2, will be the second difference, okay? It'll be easier to see this by example. So here's a table of a quadratic. Found the first difference, found the second difference is 6. So I know it's a quadratic. Now we need to figure something out. So I know that 2A equals 6. That means A equals 3. I know that C equals negative 3 because that's our y-intercept. So I'm left with this equation here, 3x squared plus bx minus 3. Well, we need to find b. So what we're going to do is we're going to say, okay, when x equals 1, sorry you guys, I screwed something up here, I messed it up, but I will fix it and fix this problem. Okay. No, I did not mess it up. I was looking at the wrong thing. Okay, so bear with it. When x equals 1, g of x equals 2. I was looking up here before. When x equals 1, g of x equals 2. I just have that from my table. So I'm going to plug in 1 for x. So 3 times 1 squared plus b times 1. Okay, and I get 3 plus b minus 3 equals 2. Okay, because again, that's where x equals 1. 3 minus 3 is 0, so I'm left with b equals 2. If it was some other number, I would just solve a two-step equation or one-step equation there. So I know b is 2. Final answer: a x squared plus bx plus c. A is 3. 3x squared plus b is 2. 2x minus 3 is our c value. Thanks for your attention, guys.